All right, let's dive in. Today, we're talking about one of the coolest and honestly most powerful tools a physicist has, dimensional analysis. You can think of it like a secret decoder ring for the universe. It's a way to check our work, and you won't believe this, even build physical laws right from scratch.
But before we get into the nitty-gritty, let me ask you something. Look at this equation. Force equals mass times time. Does that feel right to you? Something about it just seems wrong, doesn't it? But how could you prove it's totally impossible without plugging in a single number? Well, stick around, because you're about to find out exactly how. You see, the best way to wrap your head around this is to think of physics as a language. And if physics is a language, then all those equations we use are its sentences. And just like any sentence, they have to follow certain rules, a certain grammar, to actually make sense. Dimensional analysis? Well, that's our grammar checker. It makes sure our physical sentences aren't just a bunch of nonsense. So if we're going to check the grammar of physics, we need to start with the alphabet, right? And here's the amazing part. Every single thing we can measure in the universe is built from just 7 fundamental building blocks. But first, what do we even mean by a dimension? It's not about the number. It's about the kind of thing you're measuring. It's the basic quality of it. For example, a distance has the dimension of length. It doesn't matter if you measure it in meters or miles or light years. The number changes, sure, but the fundamental type of thing it is, length, always stays the same. And here it is, the complete alphabet. Mass, length, time, electric current, temperature, light intensity, and amount of substance. That's it. It's kind of wild to think that every concept in physics, from gravity to electricity, can be described using just these 7 fundamental ideas. So once you have the alphabet, what do? You start making words. Take velocity, for instance. We all know that's just distance divided by time. So in our dimensional language, its dimensions are length over time, or LT-1. Acceleration, that's just length divided by time squared, or LT-2. See, we're just combining our basic letters to build more complex words. All right, we've got our alphabet, we've got some words. Now, let's check some sentences. This is where we get to use our first big rule to make sure an equation actually makes any logical sense. This brings us to the absolute heart of the whole thing, the principle of homogeneity. It sounds fancy, but it's really just a formal way of saying you can't add apples and oranges. You can't add a distance to a temperature and expect a meaningful answer. For an equation to be valid, every single piece of it, every term has to have the exact same dimensions. Okay, let's get our hands dirty. We're going to take a look at a classic from first-year physics. Final velocity equals initial velocity plus acceleration times time. We're going to follow a really simple 3-step process to check its dimensional grammar. Let's break this down. On the left side, we have final velocity. We already know its dimension is LT-1. Easy enough. Now on the right side, the first term is initial velocity, which is of course also LT-1. Then we have acceleration, LT-2 multiplied by time, t. When you multiply those, the t to the -2 and the t to the +1 combine to give you t to the -1. So that last term is also LT-1. And boom, there you have it. The equation totally passes the test. It's dimensionally correct. Our physics sentence makes perfect grammatical sense. It's an incredibly powerful sanity check you can run on literally any equation you ever come across. Okay, checking equations is cool and all, but what if I told you we could use this exact same logic to actually build an equation from pretty much nothing? This is where dimensional analysis stops being a proofreader and starts being a co-author. It's pretty amazing. So let's try this with a real example. Finding the formula for how long it takes a simple pendulum to swing back and forth. Step 1 is just to make an educated guess about what factors might be important. We'll assume the time period t depends on the mass of the bob, m, the length of the string, L, and the acceleration due to gravity, G. Seems reasonable, right? Step 2, we translate our guess into our dimensional language. On the left, the time period just has the dimension of time, or t. On the right, we swap out mass for m, length for L, and gravity, which is an acceleration, for LT-2. Now to figure out how they're related, we give each one an unknown power, A, B, and C. They're just placeholders for now. They'll tell us how much each part matters. And now for the really clever part. We use that principle of homogeneity again. We know that the total power of mass on the left side has to equal the total power of mass on the right. And we do the same thing for length and the same thing for time. This simple rule lets us build a little system of equations to solve for our mystery exponents.
So we solve that simple system of equations for a, b, and c, and when we plug those values back in, look what happens. The structure of the formula just reveals itself. It turns out the mass doesn't matter at all, and the period is proportional to the square root of the length divided by gravity. We just derived a physical law using nothing but logic. It's kind of like magic.
But, like any good magic trick, you've got to understand its limits. Dimensional analysis is an absolutely incredible guide, but it doesn't give us the whole story. So here's the fine print. In our pendulum example, the real formula has a 2 pi out front. Our method completely missed that because 2 pi is just a pure number. It has no physical dimension, so our grammar checker can't even see it. It also can't handle things like sine or cosine functions. And here's the big one. Just because an equation is dimensionally correct, that isn't a guarantee that it's physically correct. It's a vital first step for sure, but it's not the final word. Ultimately, dimensional analysis really shows us that physics isn't just some random collection of formulas someone memorized. There's a deep, beautiful, logical grammar holding the whole thing together, making sure the universe is consistent with itself. It's a powerful reminder that there are these hidden rules all around us, just waiting to be discovered.